So exceptions were discussed yesterday with these examples. Let's create a new file and then repeat them. Basically, so if any error happens in a program, let's say a divided by 0, the computer cannot compute 1 divided by 0 because it's going to be an infinity. And in our programs, we might get into so many problems or error scenarios. So the way it does programs execute is, let's say I have a print statement already. After the error statement, so this is definitely going to have a problem. So this, as soon as this calculation is done in the CPU, it will exit the program, it will error out, and this is not computable. And whatever statements that we write out of it or after it will not get executed. So in situations where we are running some kind of service, if a client request fails due to an error, server should not come out or exit. So in that type of scenarios, we could have to handle these errors gracefully and return the error to the client and continue serving to other clients. So let's try to execute this file. Start file. So as soon as this 1 divided by 0 error is happening and it's not continuing to print this statement, it's coming out of this execution loop. So in order to handle these type of issues gracefully, we use blocks called try except blocks. So this except accepts a type of exception. So exception is a parent class of all exceptions. So basically, this is a generic error handler for us to handle all types of errors. Anything that breaks can be a divide by 0. This is especially a divide by 0 error. So either it is a divide by 0 error or key error, whatever it is, this exception class is called to catch it. And we are actually saying that if any error happens, just do this and continue executing the program. Let's run this. So this statement got executed because we had a zero division error here introduced, and it continued execution. So if I want to see what is the exception is all about, what type of exception happened, so I can accept that as a parameter, as x, or I can just put it as b. So any variable in the case. So I can print this ex here. What's this? Ex is over there. If I print this, I have to use an exception function. How to use this syntax. So it has printed division by 0 error. Basically, what it's saying is, if I just do print type x, it will give me what is the actual class type of this error. If zero division error. If I don't handle this like this, it's just put this block and this one can try to do this error. So good. And by default, Python prints the error type along with the description of that error. So the description is a string representation of this error, division by 0. When we tried printing that error object here with this, we actually got division by 0. This is the string representation of the error or exception. So error and exception are one and the same. Some error happen, and the description of the error is printed as x. And the type of the error is division by 0 division error. Suppose I have few other lines. Let's say I'll come into this and I'll do one operation that is add a number and a string. Let's see what the type of error is. So if the type of error is type error, and the message that it is giving is the error message is unsupported operand types for plus integer and string. So basically, we can handle different types of errors based on each type of error. We have custom logic to execute that can be done with multiple except statements. Let's just add those except statements. Except zero division error. Something. And similarly, if I encounter a type error, in general, if apart from these two exceptions, if any other exception happens, this block gets executed. So this is a generic handler for all types of exceptions. And the more specific exception types should be put before this except block. So the generic exception type, if we use in the first, this when the program is getting executed, it will see if there is an error. It will first check what's the first exception that we are having. Okay, this is not matching zero division error, so I go to the next one. Is it matching type error? So then execute this logic, this block of code. If not, then check this. So exception, if I'm using exception as the handler, it matches all the error types because it's a parent class of all the exceptions. Zero division error, type error, all these inherit from exception class. So this exactly matches this. So if I put this condition here, no matter what the exception is, it always executes this code because this is the first statement and it is matching this exception that it's generated. So I need to always put this exception block at the end of all the more specific exceptions. Okay. So now I'm handling zero division error, type error, exception in general. So let's just put this code in a function there. So I have a function cause error. Let's just say I will pass an argument called n. I'll just do this n. I'm just going to call this cause error. This is not going to cause any error. If I call this with 0, this is going to have a zero division error with this line of code. Let's run this. So now we are getting zero division error. Let's say I have some other functions which will have these kind of errors generated. Let's say every time I have to handle this in any part of the code, I will have to repeat this try and then except block entirely. There is a better way to do this. Instead of wrapping this entire thing in every time we want to handle, we can wrap this entire function within a decorator. Decorator actually means a wrapper on top of an existing function. So when I'm calling a function, If something has to happen before and after function gets executed, that is what we use decorators for. So let's just see how decorators go. I'm just going to comment on this portion and simply explain how decorators go. So let's say I have a function definition of I. Here I'm not doing anything, or just print some statement. I. So let's say I want to wrap this function, call this function within a specific set of preconditions. Let's use this itself. If I have to wrap this under this kind of statements, try catch plots. This can be done, this wrapping code can be done in a decorator. So I will just declare a function. Decorator actually means the function itself. So let's say handle exceptions is the decorator name. It's just a plain function. First argument is going to be a function reference to it. So this is how we declare a decorator function. Decorator is also a function which accepts the argument as a function reference. So this function reference we are going to pass to handle exceptions. So inside this template of how to define a decorator is levels. I will define an inner wrapper function. And then from inside that function, I'm going to call whatever is passed to handle exception. This function, whatever is passed into this as an argument, that function I'm going to call inside the wrapper. That's it. And then I will return wrapper function. This is actually a decorator. Now I can use this decorator for any function that has no arguments passed. Let's just put this above this one. So now this is a decorator. I'm just putting a comment here. It's not necessarily decorator function. So now how do I use this decorator function on any function like this? So this name I should copy and put an @ symbol just above this function and then use that function name. This actually means this function is decorated by this handler, this function. So handle exceptions is a decorated function that is decorating this function. What this actually means is that this function reference, my function reference, is actually going to get passed as argument for handle exceptions. So when I'm doing this syntax, if I'm typing like this actually means I'm actually passing, let's say this is equivalent to handle exceptions of my function. That is what this actually means. If I'm decorating like this actually means this. Define this and then pass handle exception, call handle exceptions with my function. So whenever my function gets called, internally, this is what is going to happen. This handle exceptions function is going to get called with this function. and all the arguments that passed. So now let's execute this. So this function I'm going to use try catch. Right? Inside the wrapper, I'm going to use that try catch and call this function inside the try catch block. Try itself. Simple. Now let's execute this my function. My function. I'll just scale and my function. This is what it has. The same function. Let's do the same thing with this cause error. We want to put it below. Yeah. This function also I'm going to use handle exceptions. Now 2 times I'm using the same code format and I'm not repeating this try catch box. So instead of try except, I'm just going to put all this code to handle all types of errors so that I don't have to repeat for every function call. So this is a good use case. We don't have to repeat for every function call. We don't have to repeat this exceptions handle. Now there is a simple small error. So this function does not accept any arguments, but this function accepts one argument. So Python is going to complain about that. Let's try running it. And this cause error also we should call, let's say, cause error. It's divide by 0 error and trigger. Let's do that. So this Python complains that handle exceptions local stack takes 0 positional arguments, but 1 was. So basically what is happening here is when I call cause error with 0 as a first argument, this is actually calling handle exceptions with function argument. We are passing this also 0. It's calling cause error with 0. So this function, what we declare here, this function does not accept any positional arguments, but we are actually passing by calling this cause error function with an argument. Yes, this function is declared with one argument. This is calling out. So in order to handle this scenario, we have already seen one instance of declaring a function. Let's just revisit that. Let's say I have a definition of a function from 1 as 1 to 1 from the 2 3 arguments. Then and let's go. So now one, this is the sub. Okay. Now, if I have to pass n number of arguments instead of 1 or 3 arguments, if I want to handle n number of arguments, any number of arguments, I can declare a function with star cards which accepts a list or a tuple of arguments and then sums it up. It's called from 2, 1 to 2. So this does let's say I can pass 4 and 5 also. Any number of arguments I can pass. So that this function is able to handle any number of arguments that are passed as parameters. So that's what we are going to implement here. So in a generic way, if I have to fit this decorator to work with any type of function, I need to make sure that star args is placed here. And I can do the same thing here. When I'm calling the actual function, wrap the function, I have to pass all those arguments back to the function. Now, this one gives an empty args list, and this function gives one argument in the args list. So in generic way, we have handled it. Let's run this. So it entered and something to do with zero division error because we called this function with 0. This time, let's call it with A and do the same thing. First call is successful. I'm in my function. This function got called with the exception handling in place, and cause error got called, and because we are handling the exceptions in a generic fashion, the zero division error statement got printed. When we call the same function with A, type error happened. Because in the cause error function, we are doing the sum as well as division. So this is how we write decorative functions. This is an advanced concept of Python. You don't need to immediately understand the decorators. As you use Python, you will understand more. So leaving that out, now let's get back to the exceptions. So there is something called inheritance we have seen in class type inheritances. We can actually extend exceptions in order to have our own custom errors or custom exceptions. So how do I do that? Is by inheritance. Let's define custom exception. This is an exception, and it inherits from exception. So as I mentioned earlier, exception is a base class of all exception types, zero division error, type error, and other types. It's all child classes of exception. Exception is the base class, which is a superclass of all. Here I'm going to do nothing. Custom exception, just inheriting all the properties and attributes, functions, and every single detail of exception. So now I'm going to cause the error by tracing an exception, custom exception. And the message I can pass here, right now I'm not passing. It's try causing this error, cause error. Now, this has created a custom exception. And I can actually pass any custom message here. This is custom exception, and the exceptions message also gets printed as a trace back. So similarly, we can have exception types for multiple inheritance we can do, multiple levels of inheritance we can do. Well, I revisit this for custom exceptions. We have defined HPV exception, that is coming from base exception, and I have defined an overriding constructor in this exception that calls the super class, which is exceptions constructor with this specific message. So I'm not implementing that in this child classes, so that this is common functionality that is inherited by default. And we are extending HTTP exception in not found and server exceptions. Now I'm raising the server error. which in turn prints status code messages. So on and so forth. This is about exceptions. So yesterday we stopped discussing about threads. We haven't discussed threads yet. Let's just try demonstrating that threads. Let's say, for example, I have a long square function. Yesterday we just discussed. So this function is going to sleep for 2 seconds. This is just to simulate a long running process. Usually some square does not take much time. But if there is so much things to be done, there can be so many error statements here, and CPU will be busy doing those operations. We have to import the package for line in order to use sleep function. What this actually does is it sleeps for 2 seconds and then turns the square of the number. So I'm going to calculate this square for like 10 numbers. For I can just do with this for n in range 10. I can do long square of n. This is one way to do it. Let me do another one. Long square of n for n in range 10. This is a shorter operation. We want to print this list. Or I can do one thing. I can just do print. And then print that next. While it is calculating, we are going to print the number as well as at the end, after all the calculations is done, we're going to print the list of numbers. Let's run this code with let's takes 20 seconds because each of these long square calls is happening in sequence one by one. I'm going to call this for number 0 and then number 1 and then number 2 and then the number 4 and so on. This is all sequential operations. So this takes like around 20 seconds to complete. So what if there is a way for me to call this function without waiting for the return? So ultimately what I need is the end result of the entire collection. What's the range of numbers, the squares that we usually get. So we can make use of threads forward. Threads can be imported with a library called thread. So basically what threading or thread means, CPU is going to collect, CPU is very fast. It's hundreds of gigahertz. 1 gigahertz is like 1000 hertz. Like that many calculations it can do. So this roughly takes 10 or 20 hertz to calculate. So because we don't have to limit the compute capacity by the way we are calling the function, we can increase the performance by increasing the parallelism. So this threading library allows us to call this long square without waiting on its execution or completion. Let's figure out how to do that. I'm going to comment out this portion. So how do I create a new thread? Every thread runs in parallel. So thread, I'm going to create a variable called T1. And I'm going to initialize this with threading dot thread. And this will instantiate a thread object. So The first argument of this thread object is the target value. Target is the function name which I want to call. Long square is the function name I want to call. The second argument is the tuple of arguments. Arguments I have to pass. Currently, the argument is only one, but the syntax of thread allows you to pass a tuple object in the args. So how do I pass one single element into the args tuple? Is through like this. One comma. If I just put one comma, this actually means this is a tuple. If I don't put this comma, this Python will assume that you're only passing one value, which is wrapped in parentheses. There is no special meaning for parentheses in Python or any other language. In order to specifically tell that we are passing a tuple instead of a single value, we have to put a comma. What this means is this arguments, I'm passing a value. That value type is a tuple and it has one single element in it, which is 1. And I'll copy the same line. I'll create another thread, T2, and I'm going to call the same function, but this time with a different mode. So like this, for each n, I in range 0 to 9, I'm going to call this line. Similarly, I'm trying to call this long square function 2 times with a threading module. This time, these T1 and T2 has to start in parallel. So calculation will happen in parallel. Whereas this code executes one by one, calculates the squares one by one. This code calculates these things in parallel. So another thread I can add. I'm sorry. Now let's start these threads. So we have just created these threads. We haven't started these threads. We have not scheduled these threads to run on the CPU. We haven't even called these threads. Just created thread objects like this. So how do I start the thread? So that is through start function. Even the start means it will start only this thread. I have to start all the threads. Now, okay, this is started. So if the program comes to the halt, I mean, at the end of the line, it exits. So the problem with exiting the program is whatever threads we have triggered, they all get stopped if the program execution stops. So Python doesn't know that there are 3 threads running and I have to wait for those threads to complete. So we have to explicitly tell the interpreter to wait for these threads to complete. Threads are nothing but one independent job that is running, or a parallel job that is running on the CPU. So we have to explicitly tell Python interpreter that wait for this thread to complete. So that is through join call. So what this means is wait for this thread or this function to get executed and return it. So similarly, I have to wait on all the 3 threads. I have to wait till all the 3 threads are completed. This will halt the program, pauses the program from exiting till all these threads are completely executed. Let's run this. No, this all things have been completed. But if you see the output here, first output is 40, second output is 1, and third output is 9. But we are actually calling this in 1, 2, 3 order. So the second thread got executed or completed first, and this first thread got completed second, and third thread got completed at the end. So the moment we are starting these threads are independently running. They are not waiting on one another. If I'm triggering all these jobs in parallel, all these jobs can go in their own space. If a process or if a thread is waiting on some input or waiting on the sleep, the other thread actually can come out of the sleep and continue its operation. So that is massive parallelization in terms of threading. Same thing, let's do it with 10 threads. So I have created each thread one by issuing this, creating a new thread object. Let's do this same thing in a better syntax for 10 threads. So I'm going to use the same syntax that I used here. Let's just say threads equal to a list, threading dot thread. Target is going to be long square. Default is going to be n comma, but n in image. This actually is initializing a list of threads. So for each of them, I'm going to do one t dot start. I can do the same thing, just to do it a bit more with a for loop, just to give you context on different ways of issuing this. For t in threads, t dot start. That's it. And now we have to wait on these threads, all threads. Same thing I'll do. I can do it this way, t in threads dot join. I can do it this way, or I can do it in a more a compact fashion. We got join. That's it. Now let's run this program. So we are actually triggering all 10 calculations all at once. In that, those things can output in any order we want. If one guy is sleeping, one guy will be waking up and running in sleep. So this order is not matched. Yeah, order does not matter. Order, when we are triggering threads, order cannot be controlled. So we want, if some job has to be done independently, it can be done independently. So now let's say, yeah, that's a good question. Let's see how to get this list of numbers, squares, which numbers square is what. So we have to store that somewhere in the results, right? Let's do one thing. Let's create a results object. Results, let's call it as a dictionary. And one small correction I need to do when it comes to dictionaries is I mentioned that if I take my dictionary can have a apple, a, or like this. So I said that only strings are allowed, but that's not exactly true. The key can be even an integer also. Let's just do it integers. 1. We can have objects also, or any combined 0, 0. It's allowed as long as the key is unique any type of tool is allowed and any type of value is allowed in Python dictionaries. So this same thing I'm going to use to store these square values. So this result will have, let's say, 1 will have square of 1, 2 will have 4, 3 will have 9, like this. So I want my threads to update this results dictionary so that I can print the dictionary. Now I can print the results. As of now, we are not passing this dictionary to these threads. Let's run it now, and it doesn't print anything. This results, I need to pass it to the thread calculation logic. Long square, if this accepts a dictionary. And if I am appending the dictionary, yeah, let's say results number, rows, number, uh, it adds this and returns it as well. Now, at the end of the loop, I can actually print the results object and then get what is calculated, which value square is what. So that results object also need to be passed on the long square. So now long square earlier we was accepting only 1 argument. That's why we have used only 1 argument. This so what we are doing here, we are calling the results along with number and passing the results dictionary to this function that is called in the thread. And now I'm going to print that result at the end of all the threads of it completed. Let's execute this. So at the end, it's printing. The order did not matter here, but as long as the number key is 3 and its square is none, this can be useful. So this is how we use parallelism in order to do calculations. Let's do the same thing without using threads. If I do that, same logic will use it for 10 numbers. This executes in 20 seconds. Without using thread, it's going to take a long time. With threads, it executes in 2 or 3 seconds max. So that's the advantage of parallelism and multi-thread. So what we have done here is Okay, there is one small difference between a process and a thread. So there is, let's say, I can do the same thing with processes. It's just go to let's do this with 0 to 5 and 5 to 10. I'll just use same row. Right, and thread start with 5. So this is not using threads. I can do this in multiple processes also. Parallel connections I can do. Python threads start. Two processes running. They both are calculating independently. This process is still computing. So the difference between this two things, so the way of triggering two processes and triggering two threads is a little different. So the difference between these two is the memory that is used by threads is shared. Let's say this results dictionary is actually shared between among all the threads. So this when any thread in this program is referring to results, it actually refers to the same object, so which is shared across all the threads. When I'm processing this in a new process, that results object will itself have a different value. So memory cannot be shared by two processes. Only threads can share the same. So that's the advantage. That's the use cases where we will use threads instead of processes. We can also trigger multiple processes from within this Python code that we will see next. As of now, the main difference we need to understand is threads will have the shared memory. All variables, all objects that are stored in the program, all threads will have the same object references. So if one thread modifies this results object, the other thread also sees the modifications. So when I'm running in a different process, when one process modifies the results object, it is modifying its own copy of the results object. It's not modifying a shared copy. So that is the main difference between running two processes and two threads. So we'll get in depth into threads and processes later once we get familiar with this technology. So for now, it's just enough to know that there is a difference between the process and the let's go back and comment. This is about threads. So let's now see the processes. Now we have triggered two processes manually from the terminal. So Python, if I execute this, this is actually going to trigger a process. So the same thing we can do it within the code itself. We can have spawn multiple processes instead of spawning multiple threads. We can spawn multiple processes as well. Let's do that. So especially for handling processes, creating new processes, we have a library in Python called multi-processing library, multi-process library. For that, I need to install a package called multi-process. Multi-process. You can install multi-process. This allows us to create new, spawn new processes. So I need to import this from the process, import process. Let's import Fine. Same code and then we copy from previous code. But we have threads. Same logic. This time I'm going to copy this, but not. I'm going to demonstrate the uh, memory sharing logic. Instead of threadings.thread, this time we are going to use process here. Similar to this, we are going to use style instead of threads and then use processes as the variable name, and for p in processes without start for p in processes. This is going to start the processes and then join for p in process. Similar to what we did for threads, take our join. Same thing we are doing for process as well. So this is going to demonstrate a difference between what a process is, what thread is. Let's run this code. This time, so each of the calculation is going to happen in its own process. Let's run this and then print results. This time results module will not have actual data because results is not shared. So this results object is always going to be wrong. Let's run this. It's on processes. Right. That is a system evidence. So in introduce that see here. This is specific to Windows operating systems. In Linux, this won't happen. But process processes and range. Processes source. Similarly, process without start and then swing flash. Showing. That's there is a problem with Windows. That will be safe. So I think we have to do something like this. Yes. I will explain what this is later. Let's figure it out. Okay. Now we are starting 10 processes in parallel. So let's go back to the syntax of using this. Yeah. Now, what we have seen here, if I'm printing the results here, it's actually printed empty, even though this guy is modifying results object to add these numbers. We are still seeing the results as empty because these threads, apart from threads, processes do not share this results object, even though we are passing this results object or a dictionary. So it's actually going to make its own copy of the dictionary and then use that dictionary as we are doing the process here. It doesn't manipulate this results object because it doesn't have access to this. So the main process is different, and this child processes that we triggered are different. They don't share the memory. So that's the advantage of threads. So the main difference of threads and processes is that a process can run on a different CPU core, whereas a thread can run only on the current CPU core. So in modern CPUs, we have multi-core CPUs, right? 4 cores would come in i5 processor. So the advantage with processors is that the two processors can run in parallel in 2 different cores. Whereas a thread, multiple threads, if you are spawning from within a process, all those threads have to share the same memory space and same processor core. So it's just a simulation of parallelization when it comes to threads. In the processes, if you're running multiple processes, that is actual real multiprocessing. So whereas threads only simulate the parallelism by allowing CPU to work on some other thread while one thread is waiting on a certain operation or certain event. So these core concepts we will discuss when we go in depth into computer science concepts. So the difference is that clear now. The memory space is not shared by different processes, but only by threads. So we have to make use of threads and processes based on our use case. If memory has to be shared, if same variables need to be accessed, same data structures need to be manipulated, we will have to use threads instead of processes. So when it makes sense to have different processes, let's say to manipulate files, so having multiple files processed in parallel, that kind of scenarios we can use processes rather than threads. So that's about threads, multi-threading and multiprocessing. We can do that. I'm just adding threads.time.sleeve only to simulate a large process. Let's say instead of this time.sleeve, I can keep it. You won't see any difference. So because I put time.sleeve, we are seeing the difference. If I do it in sequence and if I do it in parallel, what visual difference you will see in real time. So instead of this, usually we will have like calculations ranging from like large number of code lines if I have to write. I'm just trying to simulate the workload that we usually put on the programs. This time.sleep is not needed. So if I just do this and comment this, basically you won't be able to see that much of a difference. whether we are using multiplexers or same process. One mechanism of the difference. This will find out. So this one you won't see any difference if I don't put this. So the parallelism that we get, the advantage of parallelism, we can only see when the process is taking too long to complete. If it's like milliseconds interval, if there is a difference, we can't observe it with our perception. So that's the reason I have like simulate a heavy process. That's about processes.